Okay, welcome to the last History of Math lecture series this semester. And this last lecture is special in three different ways. First of all, Professor Yao will be joining us in the audience because our last lecture will be about the history of game theory by world expert, leading expert in probability theory, Professor Yuval Perez. And the third thing that is unusual about our last lecture is we have our model class, Shifan Ban, of seventh graders from 101. Please welcome them. Okay, please take it.
Okay, do you all hear me? Good evening. It's a pleasure and honor to be here to tell you some highlights from the history of game theory. As Yuval mentioned, my main area is probability theory, but I've taught courses on game theory. I've written a book on game theory, and I'm actually a fan of the history of game theory, so I'm enjoyed preparing this lecture. A lot of it is based on notes in my book with Professor Anna Karlin on game theory, and I'll mention this book as we get along. Okay, so there's an interesting connection between the beginning of modern probability and the beginning of modern game theory, and that's in the person of Emile Borel, who played a key role in both. So in 1921, Borel wrote a paper on zero-sum games. So games where when one player wins, the other player loses the same amount. And each player can choose between several strategies. And if the first player chooses strategy I, the second player chooses strategy J, then the first player wins that amount from the second player. And so we have a matrix describing this situation. And they have to choose strategies, but Borel realized that it's important here to choose randomized strategies, that is also called mixed strategies. And let's start with a very simple example. Borel focused a lot on 2x2 and 3x3 examples. You know, computers were not available. So for 2x2 matrix, here's an example. We have two players, the hider here in blue, and the hider puts one coin in his left hand or two coins in his right hand. Those are his options. And so only one of his hands will have coins, either the left or the right. If it's the right, then it will be two coins. Okay, so that's the rules of the game. Now, so the chooser has to pick a hand, left or right, and she wins. So she wins the coins that are in the hand. So if she chooses left and she was correct, she will win one coin. If she chooses right and she is correct, then she wins two coins. So here's a game. How would you play? And especially suppose that you are going to play this game many times. So if you were to always play left or always play right, then the opponent will know your strategy and will win. So if you think about it, in this case, both hider and chooser have to change what they're playing as the game evolves. And even if we're playing one round, this means that you really should decide kind of randomly, are you going to do left or right? But what are the probabilities that you'll assign to left or right? This is, first example. And let's look at this as Borel did. Not at this particular example, but he looked at examples like this. So, this will be one of the few graphs in this talk. Most of it is, is history, but here's a graph. So what does this graph represent? Since we said, suppose that the hider chooses left or right with some probability x. Say x1 is its probability for left. And then we'll examine what happens. All right? So here is, so actually here is hider's choice. So we'll call hider's choice y1. So hider can choose the probability of left and right. And in each case, he considers two graphs. What happens if, so this graph represents when chooser plays right. When chooser plays right, then her payoff is twice 1 minus y1. And when chooser plays left, her payoff is going to be y1, if hider's choice is play left with probability y1. So we have these two graphs. And in this game, hider pays chooser the amount. So what hider is worried about is about the maximum of these two graphs. And he wants to minimize the maximum of the two graphs. So so he will choose the probability 2/3 for left. Now, if we look from the perspective of chooser, so chooser also looks at two graphs. So if he chooses x1 for the probability of left, then there are two graphs. When hider plays left, then the relevant graph is just x1. And when hider plays right, the relevant graph is twice 1 minus x1. But chooser is worried, chooser is going to get the amount. So he is worried about the minimum of these two graphs, and he wants to maximize this minimum. So in this example, he'll also choose 2/3. And if you see his payoff is going to be the same. So the max of the min equals the min of the max in this example. So if you want to see this example more slowly, you can, we'll have these slides available. And this example is also in the in chapter 2 of my book with Anna Carlin. Okay, so here's another example, similar flavor. Game of penalty kicks. So I don't know how many of you play soccer, but in penalty kicks, the kicker has to decide if to kick left or right, and the goalie has to decide whether to jump left or right. And here's an example of a possible payoff matrix. So the payoff represents 1 if the kicker actually scored a goal. So we assume that if the kicker and the goalie went in different direction, then the ball definitely goes in. Okay? So that's what you see here. If the kicker plays left and the goalie dives to the right, the ball will go in. Similarly, if this right and left. But even if the kicker kicks to the left and the goalie jumps there, he still might not stop the ball. And then the ball goes in with probability 50%. But this kicker has a stronger right foot, so if they both go to the right, then it's 0.8%, 80% of a goal. So again, in this situation, what their actual moves are, they will hide from each other. And the optimal thing for them is to have a randomized strategy. And the probabilities depend on the relevant parameters. In this case, how strong is the kicker with his right foot and his left foot. And again, you can draw graphs as in the previous example. And this matrix is simple enough. And it turns out that the optimal strategy for kicker is to kick left with probability 2/7 and right with probability 5/7. And whatever the goalie does, this assures probability of scoring a goal to be 6/7. And there's no other probabilities that giving a better guarantee. Okay? So this is, these are two examples, not, those are not exactly the stories given by Borel, but these are the type of games he analyzed. Okay, and he formulated the theorem. He was interested in the special case of games with some symmetry, like the games we saw. And so these are represented by antisymmetric matrices A. And he said that, and he proved that for 2 by 2 and 3 by 3 matrices of the type he was interested in, you have this min-max property. And I'll explain later what this means conceptually or philosophically, that you have this min-max. But this is an identity. Now we have a mathematical identity. We have a 3 by 3 antisymmetric matrix, and we multiply on the left and the right by probability vectors. So x, delta 3 is just the set of probability vectors, vectors of length 3, non-negative, that add up to 1. Okay? So we have this min-max equals max-min, and this is definitely not true for general functions. So if you have a function of 2 variables, x and y, it's always true that the max-min will be less equal than the min-max, but equality only happens under some further assumptions. And so that's for general functions. Borel was interested in these games where these functions are actually bilinear, because the payoff from the game is a bilinear function of the probabilities. And he asserted that this minimax relation holds for 3 by 3 matrices of the type he's interested, but wrote, and there's some approximation of the original French, and this is the English translation. He wrote, it's easy to see that once n exceeds 3, this equality will only hold in special cases. So when you read a math paper and an author says it's easy to see, think of that as a warning flag, because often mistakes are hidden under the easy to see. And this is one case of that. So in fact, Borel was wrong here. And this minimax relation holds for arbitrary matrices of arbitrary sides, arbitrary rectangular matrices of arbitrary sides. And this was proved a few years later by von Neumann in 1928. So despite Borel's statement, von Neumann actually gave a rigorous proof. It was not an easy proof that for any matrix of any size, you have equality here. This was published in 1928, but it's interesting, it was first, I think it was published in German in 1928, but it was first published, it was first presented in French in 1926 by Borel himself to the French Academy. So von Neumann sent him his solution, and Borel presented it in 1926. Then von Neumann finally published it in 1928. So what does this mean for us as we're playing a game? So again, it takes some time to really conceptualize this, but what it means is if you choose the optimal randomized strategy, so one which achieves this min or achieves this max, you can actually declare it to your opponent without losing anything. So of course, in the game of penalty kicks that you saw before, let's go back. Right, so in this game, it would be very bad if you declared, I'm going to kick left. But if you declare, because that will give an advantage to the opponent. But if you just declare the optimal strategy, namely, I'm going to kick left with probability 2/7 and right with probability 5/7, it doesn't change the value of the game. So you can reveal an optimized mixed strategy, just not reveal the results of your coin tosses, the results of the randomization. But this you can reveal, which is quite profound in its implications. Borel, when he thought there is no optimal strategy in this sense, that Minimax theorem doesn't hold, thought that game theory cannot be handled by mathematics. It should go into the realm of psychology. But von Neumann showed, no, mathematics can actually handle this type of game very well. The first book on game theory that was very influential was published by von Neumann in collaboration with an economist, Oscar Morgenstern, in 1944. And this book had a proof of the Minimax theorem, but not the original proof. I'll come to that. Anyway, as you see from the collaboration with an economist, von Neumann already saw that this should have implications beyond mathematics, and he was right. Now, von Neumann is no doubt one of the most accomplished, most famous mathematicians of the 20th century, and you surely have heard of him in other connections, building one of the first computers, von Neumann algebras, and the list is very long. I want to use this opportunity to tell you about one of my mathematical heroes that is far, far less known, and that's Jean Ville. Jean Ville was a student of Borel, who Borel assigned to read and really understand von Neumann's proof. And Jean Ville found a much better proof of von Neumann's theorem. He phrased it in terms of kind of convexity and matrices, but now we understand his proof is a case of duality. And one of the first uses of duality, appearances of duality in applied mathematics. And this is, so again, he didn't exactly, he expressed it analytically, not geometrically, but in fact, his proof, if you look at it with modern eyes, or even, not so modern, what you'll see is the hyperplane separation theorem. So this is a theorem you'll all encounter or have encountered in your studies. So important, so nice. If you have a convex set, and the origin, say the convex set is in Euclidean space, this holds in much greater generality. Banach spaces, even more general, but let's look at Euclidean space, Rn. And you have a compact convex set. Again, this can be more general than that. That's disjoint from the origin. Then you can separate this set from the origin by a hyperplane. So in the plane, all I can draw is two-dimensional pictures. So you see a compact convex set in the plane, and it's separated from the origin by a line. Okay, the origin is on one side, the compact convex set is on the other side. And this actually characterizes convex sets. So if the set is not convex, then there will be points where you cannot find such a separating hyperplane. And so this fact, in Euclidean space, it's very easy to find this hyperplane. You just find the closest point in K to the origin, find the closest point, connect it to the origin, and draw the hyperplane that slices in the middle of this normal. So it's very easy in Euclidean space, and that's really the case needed here. And Jean Ville derived the Minimax theorem in a few lines from, I said, the analytic version of this. And this actually was the proof that von Neumann and Morgenstern used in their book, not von Neumann's original proof. I mentioned Jean Ville here because in my main day job in probability, Jean Ville is one of the pioneers of martingales, which are the most, one of the key wonderful tools we have in probability. So this tool is most famously associated with Doob, but Jean Ville proved some of the key inequalities even before Doob, and Doob gives him credit, as did von Neumann and Morgenstern in their book. They give credit to Jean Ville, yet he's not as well known as he should be. Talking about duality, I want to jump a little ahead and say that linear programming, solving a system of linear inequalities, became very important in applied mathematics, in planning for operations research, in airlines planning their routes, and so on. And one of the key people in implementing that was George Dantzig in the US. Actually, he was preceded by Kantorovich in Russia, and this goes back to Monge and so on. But I'll focus here on Dantzig, who developed the simplex method for linear programming. And when he wanted to understand some mathematical theory behind linear programming. He looked in books and he didn't find, the theory he was searching for. So he made an appointment with von Neumann in Princeton and went and asked him, what can you tell me about solving this kind of system of linear inequalities? And von Neumann went to the board and showed him, a fully developed duality theory, which is now kind of a cornerstone of linear programming. And as we understand, there was such a duality theory already in France and in Russia, but to Danzig it was completely new, and he writes in his memoirs that he just sat there completely shocked when he gives the problem and already gets such a complete answer. So for those interested, I can give you, there's a citation in my book to Danzig's book where he relates this experience, and this is our attempt with the help of an artist, Nate Jensen, to describe the situation pictorially that Danzig described in his memoirs. Anyway, so von Neumann explained to him how the duality of game theory and the duality of linear programming are the same. And the duality in game theory is exactly the Minimax theorem.
Who's in the background?
What?
Who's in the background?
Oh, this is poetic license. This was in the Institute of Advanced Study, and Einstein was there at the time, but we have no evidence that he passed through the hall when they were talking. But no evidence that he didn't pass either. Okay, now game theory has its playful side, it has its, serious and even problematic side, and especially zero-sum games from the beginning were used also to model conflict. And this is an example of such a conflict, which leads to some nice mathematics. So it's just another example of a zero-sum game between an airplane, a bomber, and a battleship that it's trying to hit. Now, the battleship is maneuvering, and here we have a very simplified maneuvering. The battleship can each time decide to go right or left. That's all its decisions. So it starts here, and here it went, say it went right, and here each time it can decide to go right or left. It's generally going in this direction down, but each time it can decide right or left. The bomber, the airplane, sees exactly the location of the ship, but it takes time for the bomb to drop. So the bomb will drop 2 time units later. The bomb, will hit the water or the ship 2 time units later after he drops it. So in this game, the ship doesn't see the bomber at all. It's up in the clouds. And by the time it sees the bomb, it's too late. So it just maneuvers kind of blindly, just based on the past. The bomber sees the ship, but there's this delay. The bomber can drop the bomb now, but it doesn't know exactly where it will be 2 time units later. So this game was kind of popularized in the 1950s as it was quite challenging to solve exactly. And there were 2 papers by 2 famous mathematicians, Sam Carlin and Lester Dubins, that solved this game asymptotically when the length of time is very large. What? Yes. So they were, at Stanford and at Berkeley, and the strategies are kind of interesting here. So it turns out that again, you can solve the small games, but we're interested in these games when the horizon is very long. So the nth game is that the bomber can drop the bomb at any time between 0 and n. And we're interested in the asymptotic value of these games as n gets large. And it turns out that, again, asymptotically, the best strategy for the ship is what's called the Q reversal strategy. So it first go left or right with probability. So left probability P, right with probability Q. And later, it reverses direction with probability Q and keeps the previous direction with probability P. And, okay, and if you assume that, then let's go back. Right, so given that where the ship is now, it can move -2, 0, or 2 sites from its current location. And the probabilities are in the next slide. The probabilities are P squared Q and PQ. And so P will be chosen by the ship so that the maximum of P squared and Q is minimized. Because once P is chosen, and say the airplane can hover for a while and kind of observe which P is being used, or estimate which P is being used. And so he would choose to bomb at the site that corresponds to the maximum of P squared Q and PQ, and that's the same as the maximum of P squared and Q. So what the ship wants is to minimize the maximum of these, and the solution is 2 over 1 plus root 5, exactly the inverse of the golden mean. So it's really a straightforward exercise. This game was promoted by Isaacs, one of the pioneers of what's called differential games. And he said, well, it's very easy to see that the value of these games is bounded by this Q, which is 1 minus P, or there's the formula on the bottom. But it was less easy. But this is just restricts to a certain kind of strategy, this Q reversal strategy. But the ship could do anything. So it was not so easy to show that, in fact, this strategy for the ship is asymptotically optimal. And this was done in 2 separate, both brilliant papers and completely different proofs by Carlin and by Dubins. So, it's a nice example mathematically coming from this rather grim situation. Okay, so the next breakthrough came when Nash saw that one can and should go beyond these zero-sum games to more general games where the players are not in such direct conflict. So there's 2 matrices, A and B, and when player 1 chooses I, player 2 chooses J, the payoffs are not negatives of each other. If player 1 has payoff Aij, player 2 has payoff Bij. So the zero-sum case is a special case, but it's really a very special case. And he defined the notion of Nash equilibrium. I'll write it in the formula in a moment. But what a Nash equilibrium is a strategy which can be pure or mixed. So pure strategy, I decide what action to take. Randomized strategy, I just decide on probabilities for the different actions and then make this random experiment. So a Nash equilibrium is a pair of strategies, one for each player, which are best responses to each other. So what it means is that no player can benefit by deviating from once we fixed the strategies of the other players. So it's more involved than the concept of optimal strategy in zero-sum games. There's no such thing as optimal strategy here, but there is a Nash equilibrium. You'll see examples in a moment. Nash wrote that when he had this idea and he proved that these equilibria exist, he went to von Neumann, they were both in Princeton, to describe to him this. But von Neumann didn't like it at all. He was really stuck on the zero-sum games. He thought everything should be modeled by zero-sum games, which was a mistake of this great man. Here's a very famous example, maybe the most famous example of a general sum game. This example is very special. We'll see other examples, but still it's the most famous, so you should know it. It's called the prisoner's dilemma. And in this story, there are 2 prisoners. They're in separate rooms. They're both they're both charged with the same crime, maybe robbing a bank together. And each one can either remain silent. If there's no proof the police has no proof that they robbed the bank. So if they remain silent, all they can be charged for is some illegally possessing some weapon, and they will get, each one will get 1 year in prison. So that's this payoff, -1, -1. But if player 1 remains silent, so prisoner 1 remains silent, and prisoner 2 confesses, then the confessor gets out free, for his cooperation, and the other one gets 10 years in prison. Now, if they both confess, they both get 8 years in prison. Okay? Now, each one is sitting separately in the room. They cannot communicate. So, of course, the best outcome for these prisoners, not for society, but the best for these prisoners, is just both of them stay silent, and they just get a year and they get out. But prisoner 1 is saying, well, I don't know what prisoner 2 will do, silent or confess. But let me analyze both situations. If he remains silent, then I'm better off. If he remains silent, I'm better off confessing. I just get off free. I don't spend any time in prison. So in that case, I'm better off confessing. If he confesses, I'm certainly better off confessing because I get only 8 years in prison instead of 10. So in both cases, I don't know what he will do, but in both cases, I'm better off confessing. And the second prisoner will apply the same logic. So if they just, each one logically considers both cases, they can't communicate, so they will end up here in -8, -8. But of course, they would be better off if they ended up here. So -1, -1 is Pareto optimal. It's better for them, but it's not an equilibrium. So if if you think of the strategy as silent, then both of them benefit by deviating. So it's not an equilibrium. And the only equilibrium in this game is both of them confessing. There's no mixed equilibria. There's no confusion. The only equilibrium is the pure one where they both confess. And this was important in the history of game theory to understand this game. Here's a less negative version of the same game. Something that occurs in many, many situations. So again, we have 2 players, and they can, now they're not prisoners. They just can, cooperate, building something good together. And if they cooperate, they will both get 6 units. But, if but each one of them could build this themselves. So if player 1 tries to cooperate and player 2 defects, player 1 will do all the work. It will be built, but he will get what he wanted to build, but he will put so much effort that for him the payoff is 0. Player 2 will get what he wanted built. He will put no effort in, so for him the payoff is 8. Okay, and you see the other situation. Now, if they both defect, they both got to play video games. So that's worth 2, but what they could have built is not built. So this is still called prisoner's dilemma, even though there's no jail and everything is positive here. And again, it's just the same situation with positive numbers that, unfortunately, in this game, the only equilibrium is both defecting. And it's the same logic as before. I think if the other one is cooperating, then I'm better off defecting. If the other one is defecting, I'm also better off defecting. So this has bothered people for a long time, because it's kind of a negative conclusion. Now, one thing that was suggested early, well, the reason we know that in practice, in successful societies, people do cooperate and do build things. So, well, sometimes the matrix is not like this. That's one explanation. But sometimes the matrix is like this, and people still cooperate. How come? So one explanation was, well, people play repeated games. They don't just play a one-off game. They play a game, and then another game, and another game. And if you have a reputation of someone who defects, then people will defect with you or not want to play. So that's one explanation. But this explanation still needs a refinement, because suppose we play this game 10 times, okay, with the same matrix 10 times. What's going to happen? In the 10th time, we're just a situation of the one game. So whatever happened in the previous 9, we were nice to each other. Now in the 10th game, there's no more. In the 10th game, it's just like one game, so we should both defect. That's the only equilibrium. And once we do this analysis, we're both smart, then we figure whatever we did in the first 9, in the 10th game, we'll both defect. And now the same logic will be applied in the 9th. So since we know in the 10th game we'll both defect, there's nothing we can do about that. Then in the 10th, then the 9th is really the last interesting game. And then by the same logic, the 9th one will also both defect. And backward induction shows that the only equilibrium, even if this game is repeated 10 times, the only equilibrium is both of them defecting the whole 10 times. But again, it's a puzzle. People don't be, if you actually take 2 random people, assign them this game, you know, and they get paid according to what they get, they will not always defect. They will not play this unique equilibrium.
You want to maximize the sum.
Well, but, okay, fine. If you want to maximize the sum, in the last round, you should defect, definitely. That will do better.
Sure.
Okay, so you know that. So you know that I know that, so I will also defect. And so there's a more interesting explanation. We'll come to it later in the lecture. So I'll say the hint is that we don't know in real life, games are never specified to be exactly 10 rounds. We don't know how many rounds we will play. And this uncertainty is key to the solution of this prisoner's dilemma paradox. I'll come back to that. And Aumann and others got Nobel Prizes for understanding this stuff. Okay, let's continue. And we'll come back to repeated games later. Let's go back to one-off games. Here's another game that models a lot of real-life situations, and it's called the stag hunt. So whenever we see a matrix with this form, it's called the stag hunt. So what's the story? So there are 2 hunters. They're chasing this stag, which is a fancy name for a large deer. You see the stag in the background right there. That's this large deer they're chasing. However, they need to cooperate to hunt this deer. One from this side, one from that side. If they cooperate and hunt the deer, the stag is worth 8 units. So they will share it and each get 4. But as they're hunting, a little rabbit, a hare, runs by, and each one realizes they could just catch this hare by themselves. If a hunter catches this hare by himself, he will get 2. The other one will get 0. He won't get the hare, and he won't be able to catch the stag. If they both go after the hare, of course they will catch it, and they will share, and each one will get a measly 1 unit. Okay? This is different from prisoner's dilemma. Here we actually have 2 equilibria. So if both of them, so we have 2 pure equilibria, both of them following the stag, this is an equilibrium. So again, what does it mean to be equilibrium? It means that neither player benefits by unilateral deviation. Okay? But both of them sharing this hare, this kind of point, is also an equilibrium. Both of them running after the hare is also equilibrium, because if Yitwa and I are both after the hare, then if I deviate by myself and go chase the stag, I'll get nothing from it. So we have 2 pure equilibria here. And there's also some strange mixed equilibrium where both players select stag with probability 1/3 and hare with probability 2/3, and they get payoff 4/3, a little better than this one, but very far from the optimal equilibrium, which is 4/4. So it's very different from, you see, in zero-sum games, there is a value of the game. You might have more than one optimal strategy, but there is a unique value if both players play optimal strategies, and the only equilibria is when both players play optimal strategies that correspond to this min-max. These are the only Nash equilibria. And there is a value that's common to all these equilibria in the zero-sum case. Here in the general case, we see there are multiple equilibria. And a lot of the development of game theory after the 1950s is theories how to select between the different equilibria. How to maybe direct people to the better equilibria. But one thing you have to understand, if you try to direct people to something which is not an equilibrium, this will be very hard because they'll keep trying to deviate. So the only things that are stable are equilibria. And here's some formal definitions. So again, we have two payoff matrices, the A and B. So, when I showed you in these pictures, I put A and B together. So here, the matrix A for player 1 is this 4, 0, 2, 1. And the matrix for player 2 is this 4, 2, is the other one, 4, 2, 0, 1. So you just take the second entries here. But in the abstract theory, we have two matrices. And a Nash equilibrium is a pair of mixed strategy vectors where, so both of them are probability vectors. They could be unit vectors, in which case we have a pure strategy. That's one case. But in general, they have to be randomized. And so X star, Y star. So what does it mean that X star, Y star is in equilibrium? It means two things, that player 1 cannot benefit by deviating. So if he changes X star to X, he won't get more. He'll get less equal. And similarly, player 2 cannot benefit by deviating. If he changes his Y star to Y, he'll also get less. This is B, which is player 2's payoff matrix. And so this, Nash did this basically in his thesis in 1950, and he gave two proofs in 1950 and 1951. And Nash is famous in mathematics, not just for this. He did work which mathematically is much deeper, breathtaking in PDE and geometry, but still this very simple realization that this is the right definition and that this Nash equilibria always exist. So there always is at least one. This has had maybe the most impact, but he is justly celebrated for many insights. He got the Nobel Prize in '94. By the way, economists have a kind of tricky Nobel Prize. So, the original Nobel Prizes were for math, not for math, were for physics, for chemistry, for biology, and, and these are the most famous prizes. So economists wanted one of their own as their subject developed, but, they were not mentioned by Nobel originally. So what did they do? They found some banks that were willing to donate the money, and then these banks, but they couldn't call it a Nobel Prize, so they called it a prize in memory of Nobel. Why in memory? Why are the economists memorializing Nobel? He was not an economist, but they figured that people will forget the memorial and will just call it a Nobel Prize, and they were right. So people just think of this as a Nobel Prize in economics. Of course, one key is that they really gave it to a lot of worthy people. So this prize, became appreciated not just because of the name Nobel, but also because of the people who got it. But still, this trick worked. Now, of course, when mathematicians wanted to do the same, we couldn't find the donors who would do whatever we wanted. So mathematicians found, the Norwegians to donate the prize, but couldn't call it Nobel, so called it Abel. And maybe someone hoped that Abel, Nobel sounds close enough, but it didn't quite work. So society, in society at large, Nobel Prizes in economics are mentioned together with the Nobel Prizes in physics and chemistry, seen as equivalent for people in general, while the Abel Prize, which we know is extremely hard to get and represents amazing accomplishment, is far less known outside math. Anyway, that's a little side story. Nash is one of the is maybe the only one who got both. Nash was actually here in Beijing in 2002 in the ICM. So this is a picture from the 2002 ICM in Beijing. And this is an enlargement of the little left corner. I was lucky enough to be in this corner. This is Noga Alon. This is Nash and his wife in 2002. So shall we do a break or continue?
Yao usually just goes right through.
Okay. What?
I have a female with Nash.
Yeah, in 2002, I see. Okay. So anyway, so that was, so I definitely remember that. That was my own first visit to Beijing. Now, I mentioned Nash had two proofs of his theorem, and they were based on two fixed point theorems, and I want to highlight those theorems. So, you know, there are game theory courses these days taught in economics department, even in political science departments, certainly in computer science departments. But I think really we mathematicians should not give game theory away. You know, it started in math, and you know, despite its great applications, it's still a wonderful motivator for math. In particular, it's one way to appreciate these even older math theorems. So Brouwer's fixed point theorem. If you have a continuous mapping from a compact convex set to itself, again, many generalizations, but this is probably the most famous fixed point theorem. A continuous mapping from a compact convex set in Euclidean space to itself always has a fixed point. And notice that you can't drop these requirements. So if the set, you know, say the real line is convex, but the map x goes to x plus 1 doesn't have any fixed point. And you know, the circle is compact, but if you rotate, there's no fixed point on the circle. You need the full disk to get a fixed point. So this theorem, you know, really needs these conditions. And Nash's first proof, though, didn't use this fixed point theorem. In 1950, his first proof used a fancier fixed point theorem due to Kakutani, which is about set-valued mappings. So I won't go into this theorem. It's a generalization of Brouwer's fixed point theorem to maps that take points to sets. They should have a closed graph. And then a fixed point for such a map is just a point x where x belongs to its image phi of x. That would be a fixed point. And so Nash's first proof used this theorem. And again, since I'm showing pictures here, this is a picture I also showed before. This is Kakutani in a conference in honor of Roy Adler, his student's 60th birthday. And, you know, and I was there too. So anyway, that's Kakutani. But that was Nash's original proof in 1950. In 1951, he published a second proof just using the the Brouwer theorem, after David Gale actually contacted him and said, well, you know, you should really prove this based on the most basic fixed point theorem. It's possible. So Nash actually published it this way. And really, and this proof is very instructive. You can find it in many places, including in my book. So the idea of Nash is that if something is not in equilibrium, then you know, you can find some improvement, and if there's no equilibrium, then he constructs a map with no fixed points. So I'm not going to go into the detailed here, but it's very, very nice application. And since then, there are, you know, many other fixed point theorems with applications in economics that show how prices could be determined in a market based on demand and supply. So here are a few more examples. Yes.
Lefschetz fixed point theorem is actually different than these two fixed point theorems, and yet has not been used by economics or game theory.
So,
Lefschetz fixed point theorem.
Yes, that's a good point. Let me check on that and get back to you.
I think you guys should try to find a good
Yes, that's, thank you. So here are a few more examples that illustrate. So here is a game of diplomacy. So you have, or a game of war and peace. So you have two countries, and each country can choose either diplomacy or attack the other country. So it's not a zero-sum game. If they both choose diplomacy, both peaceful, they both have 2 units. If they both attack each other, they both get -1. But if one tries diplomacy and the other one attacks, then the attacker actually gains some relative advantage. He's not very well off in this matrix. The attacker will get 0, but the one who tried diplomacy and waited gets a -2. So again, in this game, you have 2 pure equilibria. Both diplomacy is in equilibrium, but also both attacking is in equilibrium. So if you check on it, if both are attacking each other, deviating from that will be punished. So these are 2 equilibria. One is clearly preferable to the other, but both are equilibria. So this brings us to the theory, how do you select the good equilibrium? Now, there's also a mixed equilibrium here, but in fact, this is exactly the same matrix as in the stag hunt, just we subtracted 2 from everything. So if you go to the stag hunt and just subtract 2 from every matrix entry, you'll get the diplomacy story. So of course, subtracting a constant from everything doesn't change strategies at all. So the same basic matrix up to a constant can represent very different situations.
Can you turn it into a zero-sum game?
No. No, you cannot turn it to zero-sum game. So this is fundamental. And this is where actually von Neumann went wrong. When Nash came to him, he said, well, you should just turn everything to zero-sum, but you cannot. So here's another game example of some version of prisoner's dilemma in nature. So if you ever see nature movies, you see these gnus. They are, sometimes, attacked by a lioness. And what usually happens is when the lioness runs, all the gnus are running away. And these gnus, are quite powerful. Okay, each one is weaker than a lioness, but if 10 of them would, make a solid wall, they're very likely to defeat the lioness. But they rarely do that. More powerful animals like bulls do it, but these gnus typically don't do it. And they just run off. And the reason, well, a simplification of the reason is this situation that looks good for them, it's not an equilibrium. Because if these 10 are facing off the lioness, one can say, the other 9 can do it almost as well. Let me just run off and let the other 9 handle the lioness. And then this one is quite safe. These are each taking a risk, smaller than in this picture when they're running away, where one of them will be caught and eaten. But still, each of them is taking a risk. So this thing, which is better for all of them, if they cooperate, but it's not an equilibrium. So you don't see it. You see it in more powerful animals where one of them is almost as strong as a lioness. But not in these weaker animals that need this kind of cooperation. Now, since the time of Nash, game theory is a huge subject, and in this lecture I can only give you some hints of later developments. One of the most important ones is the role of information in games. And actually, Akraloff, one of someone I knew when I was in Berkeley, he got a Nobel Prize for understanding the information situation in used car sales. So he got a Nobel Prize for understanding why we think of used car salesmen as sleazy. It's because they have information we don't. Anyway, but here's a related example of the fish seller. So we come to the fish seller and we wonder, you know, is the fish there fresh or not so fresh? The seller does know that. So, you know, we can ask him, fresh or not fresh. Then he can answer us. His answer may be true or false. So, you know, sorry, I jumped ahead. So this creates what's called in game theory information sets. So this game tree represents the different situations after the moves of the players. But the customer here has to move, but the customer doesn't know where in the game tree she is. So this is the line where so nature decides, say, if the fish is fresh or not. Then the seller decides what to say. Should he say fresh? Should he say fresh or old? If the fish is fresh, he definitely says it's fresh. If the fish is old, he sometimes still says it's fresh. So the customer, you know, is either in this node or in this node. So this is called an information set in game theory, where you know, where the player has to decide what to play without knowing where in the game tree she is. So, you know, there's an interesting theory for that. It's called games of imperfect information, developed by multiple people. I'll tell you about that later, games of imperfect information. Then, you know, game theory started as analyzing actual games, like poker, and with the economic connection. Later, a surprising connection emerged to biology. And this answered the natural question, because if we think of randomized strategies, how do people compute randomized strategies? How do they find them? You know, is computing strategies hard and so on? But then it was found that actually a game theoretic perspective explains a lot of interactions in nature, and randomized strategies can be employed by a species using mutations where different elements, where different organisms in the same species employ different strategies, and the strategies that are more successful, you know, create more offspring. So we get some evolution of games, you know, evolution of strategies in nature. And this evolutionary game theory was really started by a paper by the mathematician George Price and the biologist John Maynard-Smith. Smith later wrote a book about this. And, you know, there are many examples. I don't have much time, but here's one of my favorites, which is both game theory in nature and an example of what's called signaling. So for a long time, observers noted that antelopes can do this high jumps in the air, and they wondered why they do that. So suddenly an antelope will jump, it's called stotting, very high jump. And then they noticed that the antelopes tend to do that when they notice a lion or another predator nearby. So first they thought maybe they're doing it to signal the existence of the predator to other antelopes. But, you know, that didn't make too much sense, because why are they, maybe the other antelope, they prefer that the other antelopes be chased than they are chased. And also they saw that this behavior happens even if a lone antelope, just all by itself, no other antelopes inside, it sees a lion, it can do this jump. So then they realized it's actually signaling to the lion. It's signaling to the lion, A, that it saw it, and B, that it's strong and healthy, because this high jump, it doesn't cost much energy from the antelope. It's much easier than, so if there's actually a chase, the chase costs a lot of energy, both to the antelope and the lion. So both of them would rather avoid this kind of chase if it's fruitless. And the antelope, by this jump, signals, spending very little energy, signals that to the lion, forget it. You know, I see you, I'm faster, I'm healthy, look for somebody else. And so this signaling also indicates that the game between the lion and the antelope is not zero-sum. See, we naturally think of it as predator and prey, zero-sum. No, it's not zero-sum, because they both prefer a situation where of no chase to a situation of a fruitless chase. So if there's one outcome that both players strictly prefer to another outcome, it means it's not a zero-sum game. And indeed, signaling only happens in games that are not zero-sum. In the zero-sum game, there's never any point to signal anything to the opponent because our interests are completely opposed. So, you know, he should just ignore my signal. But in this case, it's not zero-sum. The signal, you know, the interests are very much opposed. It's close to zero-sum, but it's not zero-sum. And so signaling can be useful. And there's lots of studies of signaling also in economics, how people signal that they're, you know, that they're rich by some behaviors and so on. And Mark Spence, you know, and Spence got a Nobel Prize for really a deep analysis of signaling in economics, but I won't go into that. And I'll mention one more example from biology related to rock, paper, scissors. You all know the game rock, paper, scissors, right? And where, you know, the rock beats the scissors beat the paper beats the rock. And if you play this kind of dynamically, like you think, you know, maybe one day if I play paper, then scissors will beat me, and then the next time maybe more people will bring scissors, and then the next time more people will bring rocks, and so on, and you get some kind of cycling among these three options. So this is pretty simple to analyze. And then people found that this happens in nature with this three types of males in this lizard. So there's the yellow-throated lizards of the same, they're all from the same species. But the yellow-throated males, they basically mate with one female. And they're very, you know, at the time, they're kind of weak. Then there are the blue-throated males. They have, you know, small groups of females they recognize the females in their group. and they generally beat the yellow ones. And then the orange ones, they're the most aggressive. They have big groups of females. They don't recognize the females in the groups. And then the yellow ones, who look just like the females, they trick them by going into this group of females, pretending to be a female, and, you know, mating with those. So what they found is that these three-type cycles, so you have 1 year mostly blue-throated, the next year mostly orange-throated that are more aggressive than them, and then the next year back to yellow and so on. And they observe this cycle, which is just like the cycle you would get in rock, paper, scissors. And this was discovered after the book by Maynard-Smith was published, and when he was told about this example, he said, these lizards must have read my book. Okay, so remember we talked about this positive version of prisoner's dilemma, cooperative defect, and what's the explanation of why do people cooperate in such a game when it's repeated? And one answer, again, you know, reality is always more complex than mathematical models, but mathematical models can give us a lot of insight. And here is, so this is the theory of repeated games with a random number of repetitions. And here we're going to assume it has a geometric distribution. So this means that we're going to play the game until, you know, again and again, but each time we only have some probability beta of repeating again. So maybe I'll show this in the next slide. So after each round of play, we play another round with probability beta. Okay, so this is repeated prisoner's dilemma, but not a fixed number of times. Okay, and it turns out that in this iterated prisoner's dilemma, which doesn't have a fixed horizon, but rather a random horizon, there are equilibria that are not defecting. But always cooperating is not an equilibrium, because always cooperating is just going to induce the opponent to always defect. So here is an example of a equilibrium. It's not the only one. There are many equilibria, but equilibrium is called the tit-for-tat strategy. And this is it's very simple. Cooperate in round one, and for every later round, play what the opponent played in the previous round. So if the opponent defects, he will get a defection from me next round. If he goes back to cooperating, then later I will also go back to cooperating. But there's a delay. And if both players play tit for tat, that is an equilibrium, provided beta is large enough. So in this case, 1/3 is enough. The exact threshold depends on the exact payoff matrix. But for this payoff matrix, so here's an example. Player 1 just plays tit for tat. Player 2, so they start cooperating. Player 2 deviates. So in this round, without provocation, he defects. So then player 2 will defect the next round and defect until player 2 goes back to cooperating. And then later, player 1 will go back to cooperating. So you can show in this example that player 2 who defected here, who deviated from tit for tat, will get punished for that. So both players playing tit for tat is an equilibrium. Now, it's not the only equilibrium. Another equilibrium is called the Grimm strategy. I start to cooperate, but if you defect even once, I'm going to defect from now on till eternity. And if both of them play this Grimm strategy, it's also an equilibrium. So there are multiple equilibria. But there was a very interesting experiment by Axelrod in the 80s. He asked many people to send in computer programs with strategies for this game of iterated prisoner's dilemma. And so he had like 40 programs. And then he paired them off at random. And there were some very complicated strategies there. The players can't communicate, but they can communicate via their play and so on. So, and there were a lot. And tit for tat won the tournament. So it got the highest number of points, even though there were a lot more sophisticated strategies, including this Grimm one and so on. So strategies that punish too heavily, they don't get many points. So, so then after that, he ran another tournament, so people knew that tit for tat won the first tournament. So they devised strategies designed to beat tit for tat. And in the second round, still tit for tat won. So there's a book about that by Axelrod called The Evolution of Cooperation, quite interesting. Okay, so again, many people contributed to this understanding. I can't list them all, but I want to, in particular mention Robert Aumann, who developed the theory of repeated gains with imperfect information and wrote a book on that with Maschler. He also developed the theory of correlated equilibria. So Nash equilibria involve independent choices by the player, but there is a way to correlate equilibria and get different kinds of equilibria. Again, this was developed by Aumann, and he got the Nobel Prize for that in 2005. Some of the most interesting work on that was done for the Rand Corporation, and it was considered state secret in the US because it was used in kind of negotiations on nuclear disarmament. So this only got published in 1995, more than 30 years afterward. And this book by Aumann and Maschler is absolutely fantastic. So I highly recommend it. At the same time as Aumann got his Nobel Prize, Thomas Schelling got a Nobel Prize. And Aumann was a mathematician. He actually started in topology and not theory and moved later to game theory. Schelling was, didn't do much math, but he had a lot of important insights, including focal points, how to choose one Nash equilibrium over the other. He has several interesting books. Strategy of Conflict is one of them. And also he wrote about games with yourself. So he gave an example that, before he's traveling to give a talk in some city, he can book a hotel room, and he's willing to pay extra for a room without a TV. Because he knows that if there is a TV in the room, he will switch it on. And he doesn't want to have that option. So it's a game between him now and his future self, who will be more lazy and open the TV. And he now wants that future self to work, not open the TV. So he has more elaborate examples of games we play with our future selves. We try to limit the options of that future self. And then the future self tries to break out of those options, break that box of cookies that was put very high up on the shelf and so on. Anyway, he got a Nobel Prize for these kind of conceptual insights that are deeper than the example I can give here. I want to move on to a topic of stable matching, another one of my favorites. So this is a paper started by a paper by Gale and Shapley, David Gale from Berkeley, Shapley from UCLA, and they defined a stable matching is a matching. So we have, in the simplest example, we have n men and n women, but in the general applications, these would be maybe workers and jobs, or colleges and students, and so on. And an unstable pair would be, in this case, a man and a woman who are not matched but prefer each other to their matches, okay, as you see in the picture. So what's the setup? We have, a bipartite graph, in this case illustrated by men and women, and each man has a preference order on the women, so it's illustrated in this picture. And each woman has a preference order on the men. And a matching is unstable if a man and a woman that are not matched to each other prefer each other to their designated matches. So this notion was defined by David Gale, but he didn't know, is a stable matching always exist? So he asked various people. No one could answer him. And then he sent a letter to Shapley, and Shapley, by return mail, sent him an algorithm that finds a stable matching. The algorithm, now known as Gale-Shapley algorithm, is quickly described. Each man first proposes to the first woman on his list. The women all collect their proposals, reject all but the top proposer. To the top proposer, they don't accept, they just say maybe. All the rejected men go down their list, and some women get new proposals, and this gets iterated till every woman, when she is left with just one proposer, that's the match. And okay, I'm describing this very quickly. You can read this in the original 1962 paper. It's in the American Math Monthly, by far the most cited paper ever in the monthly. And there's also an exposition in my book with Anna Carlin. This picture is taken from there. And applying it in the different realms was not easy, because the algorithm and the details have to be adjusted to the realities of different areas. And this applications were done by several people, especially by Al Roth. And eventually, Shapley and Roth got the Nobel Prize for this, because unfortunately, David Gale died before this prize was awarded. I'm jumping to tell you about some applications I was involved in of this. So this is, I was interested in matching random points. Here, these are n blue and red points thrown at random in a square. It's actually a torus, so it's periodic boundary conditions. And here so this is the same collections of left points. On the left, you have the unique stable matching. In general, stable matchings need not be unique, but in this geometric context, they are unique. And this is the unique stable matching of blue and red points. So again, the preference is by distance. Every blue point prefers the closest red points. And every red point prefers the closest blue point. So the preferences are by distance. And when both are using the same metric, the matching is unique. That's the unique stable matching. On the right is the unique optimal matching. So it's the one that minimizes the sum of distances. And this one has to be done by some kind of central planning. And this one has no lines can cross. It's a nice geometry exercise. In the optimal matching, no lines can cross. In the stable matching, many lines cross. But if these red and blue points are independent agents, each one choosing, then the right one is unstable. There'll be a blue and red point that prefer each other and are not matched. So they say, the hell with the global optima, we want to match with each other, and they'll match, and so on. So actually analyzing what is the behavior of the stable matching is very hard. So there's some estimates in my joint paper with Pimentel, Schramm, and Holroyd, but we don't know the asymptotics of the length in the stable matching, while the asymptotics in the optimal matching are known since the 1980s. And there's related work on stable allocation, which I don't have time to go into. I want to tell you a few more highlights. We have like 19 more minutes. So, so this is the notion of Shapley value. So the same Shapley made multiple beautiful contributions. Here is an example of the glove game. It's an example of a cooperative game. So in a cooperative game, you have a population of n people. Here, there are 3 people. And each coalition has some valuation they can get if they decide to cooperate. So in this example, these are 3 people sitting. Each, there is one with a left. There's one on the left that has a left glove, this guy. And these 2 have right gloves. Okay. Now, a tourist who's very cold, goes into the store, and all he needs is one left glove and one right glove. So, and say he's willing to pay a unit, maybe 100 yuan for that, for such a pair. What will happen in this case? Which coalition will form? So suppose that, one of these sellers say, I have to go, you can take my place. How much would you pay for the privilege of taking the place of the unique guy with the left glove? How much would you pay for the unique guy for each of the guys with the right glove? Obviously, the guy with the left glove has something more valuable because it's unique, but how much? So this problem was addressed by Shapley. So the axiomatics are, we have some valuation for every subset. So in this example, the set 1, 2, 3, 1, 2, and 1, 3 each have valuation 1 because they can satisfy the tourist. And all other sets have value 0 because they can't create a pair, so the tourist is not going to pay. Okay? And Shapley says, well, in this situation, this unique left glove is a lot more valuable. It has value 2/3, and each of the other ones have value 1/6. Now, how does he come up with these numbers? So he has axioms. So he wants some value function for each player. So V is the valuation for sets, and Psi is the value for each player. So he wants that the player that doesn't add value gets nothing. So if you add this player to a set, and he doesn't change the value, then he is worthless. He wants, so that's the dummy axiom. He wants symmetry. So if a player adds the same to any set, like these 2 players with the right glove, they're symmetrical. So obviously, they should get the same. And he wants efficiency. So the total values should add up to the value of the whole set, in this case, 1. And the most delicate axiom is this additivity. If you have 2 games played in a row, one after the other, then the value of the sum of these games should be, for each player, should be the sum of the values. And it turns out that these axioms force a unique solution. And the unique solution, the Shapley value of each player, is you think of the players arriving in a random order, and you think in each permutation, what is the marginal value? What is the added value of this player? So if we go to this example, in this situation, there's only, if I have the right glove, one of the 2 right gloves, the only situation where I contribute, if I think of the sellers coming in random order. The only situation that contribute is when the unique left glove came before me, and then I come second. So there's only, of the 6 permutations, there's only one where I make the critical contribution. So that's wherefore I should get 1/6. While if we look at the unique guy with the left glove, there are actually 4 of the permutations where he makes the crucial contribution. So it means that when he comes, the deal is completed. So basically, the only bad case is if he comes first. In any other situation, if he comes second or third, he will complete the deal. So his marginal contribution will be full, maximal. So he gets 2/3, and the other gets 1/6. So you can have committees and this, and you ask, what's the power of each voter in this committee? And the Shapley value gives you some interesting estimate for that. Another thing which would take a whole lecture, but we only have 14 minutes left, is the theory of auctions, which auctions have a much longer history than game theory. But it turns out that the notion of Nash equilibrium, more precisely Bayesian Nash equilibrium, is crucial to understand auctions. So when we think of auctions, we think mostly of auction like that, of auction of a painting, or this is an auction for tuna in Tokyo. But many auctions, the bidders are not actually sitting in the same room. There's some house that was confiscated by the government or by a bank, and the bank wants to sell it, and people send in bids, and maybe the house will go to the highest bidder. So then these are called sealed bid auctions. And there are several types of them. So the most common is sealed bid first price auction. So the highest bidder gets the item and pays what he bid. Now, if that's the situation, then if you know this item is worth, say, 0.7 to you, you should not bid 0.7, because even if you win, your gain from the whole interaction will be 0. So people always, in this kind of auction, they always shade their bid. They bid below their value. And so here is one example, very simplified example. Suppose you have 2 bidders, and we don't know what their values are. Each one knows their own value, but a priori, say, from the point of view of the seller or outside observer, each of their values, say, is a uniform variable in 0, 1 independent. Of course, this is a very special case. Okay, in that case, there's so what are the strategies here? The strategies here are actually functions saying, if my value is v, what my bid is. My bid is b of v. These are the strategies. These are the functions. In this case, there's a unique equilibrium. In this type of auction, I should bid half my value. So how much will the auctioneer get? So the seller, he will get the maximum of these 2 bids. So if these values are uniform in 0, 1, it's going to be the maximum of 2 uniform variables, but half of that. And there's a missing bracket there. Anyway, the answer is 1/3. Now, there's another type of auction, which is less commonly used, but actually used in a lot of internet auctions by search engines. And this is second price or Vickrey auction. It first sounds very strange, but it's used a lot. So in the Vickrey auction, the item still goes to the highest bidder, but he doesn't pay his own bid. He pays the second highest bid. Sounds very strange. But if you think of the classic English auction, where we auction for paintings and we keep increasing the bids, if the painting is worth $1 million to me, but the next bidder, it's only worth $700,000 for him. So as the prices go up, when we reach $700,000, he will drop out. He doesn't want to bid anymore. It's worth $1 million to me, but I won't pay $1 million. I maybe will pay $700,000 plus epsilon, whatever the bid increase is. So what I'll really pay in this increasing English auction will be the value of the second highest bidder. So this can be formalized in this sealed bid format by actually making it a rule that the item will go to the highest bidder, but he won't pay his own bid. He'll pay the second highest bid. And if that is the rule, then it turns out Why is this called Vickrey auction? Because William Vickrey pointed out that if this is the rule, then your optimal strategy is just to be honest, to bid your value. There's no point to decrease or increase from your value. And this is a very nice, easy exercise to see that. And, okay, it turns out that this basic insight applies to many situations in social choice and deciding if the government should build a bridge here or build a bridge there, what kind of information should it get to make that decision. And William Vickrey got a Nobel Prize for, much more general version of this insight, which is now known as the VCG mechanism, because Clark and Groves also contributed to it. And now, let's go to this simple example of uniform bidders. So if we have uniform bidders, both in 0, 1, then in this Vickrey auction, second price auction, we already said, they should just bid their values, so V1 and V2. But the payment will be the minimum of the values, because the second price. So what is the expected revenue for the auctioneer, for the seller? It's the expected minimum of 2 uniforms. And here we find a strange coincidence. The expected minimum of 2 uniforms is 1/3, which is the same as half the expected maximum of the 2 uniforms. So the revenue of the seller in both mechanisms is the same. You can wonder, is this a result of just this special uniform assumption, or that we have 2 bidders? And the answer is no. It's a very general thing, and this was discovered by Myerson and others, that it's called revenue equivalence theorem. That if the rule for allocating the item is the same, so if the natural rule, first bidder gets the item, then the auction mechanism doesn't matter. In Bayes-Nash equilibrium, the expected revenue of the seller is always the same. Now, there are a lot of assumptions here, like that the valuations are independent. So this is just kind of a first approximation in the simplest model, but it's still a very useful observation. Another kind of auction mechanism besides the first price and second price is something strange called the all-pay auction. So everyone makes a bid. The highest bidder gets the item, and then everyone pays whatever they bid, even those who got nothing. Now, it looks strange. Why would anyone participate in such an auction? But in fact, this happens very often. So if the government wants to someone to build a building, it might make an auction, and every architecture firm will work hard to prepare a proposal. So this preparation time is the payment. So they all pay. The one who prepared the best one or worked hardest to prepare will win, but everyone will pay this effort of preparing their proposal. Anyway, all-pay auction is another version, and Myerson showed that if the allocation rule is fixed, then different auction formats don't matter for the expected revenue. But he also did something else. He said, well, you can improve things by changing the allocation rule. So something that was already in use in practice long before is called the reserve price. So the auctioneer is saying, I'm not always going to award the item to the highest bidder, because if the bid is too low, I'm just going to keep the item. Now, at first, you might think the auctioneer does it because he wants to use the item again, and that's sometimes the case. But it turns out, even if the item is thrown away, it's still better to have a reserve price than no reserve price. So Myerson proved a very general theorem of this type that you can read about, a simple version in my book and a more general version in books specialized to auctions. But here's the simplest case. When we have those 2 uniform bids, it turns out better to put a reserve price of 1/2. So what I'm saying is, if no one bids below 1/2, I'm just not going to give the item to anyone. If someone bids below 1/2, I'll pay the second highest then the highest bidder will get it. But at the second highest bid, what does the second highest bid mean here if only one exceeded the 1/2? The second highest means the reserve price. So if one bidder bid 3/4, one bidder bids 1/4, then the one who bid 3/4 will get the item and will pay 1/2, the reserve price. So this turns out to be an optimal auction. So there's no way no rule the seller can make that will extract more revenue from these two bidders than this very simple rule. And there are a lot of very complicated rules you could make, multi-round and so on. This is optimal. So this is Myerson's theorem, for which he got a Nobel Prize in 2007. This is a nice example by Dawkins where it was observed that penguins will stand on the ice for a long time, very hungry, and then one of them will jump in, and with, say, probability 10%, he just gets eaten right away by some leopard seal lurking or some shark. And probably 90%, he starts to eat, and then the other penguins also jump in. And this can be understood as a type of auction called the war of attrition auction. Again, I don't have time to give more of this example. I want to end with a few connections of game theory to other subjects. So when I arrived in Berkeley in 1993, I wanted to teach a course on game theory. I learned a lot of game theory in Israel, and I thought it's a nice change from teaching probability all the time. And that course was already on the books because David Blackwell had taught a course in Berkeley, because he found in the 1960s strong connections of game theory and statistics and decision theory. And his insights on that connection led to fundamental theorems in statistics, which I can't go into right now. But I remember, as a young faculty member, telling him, well, I'll go quickly through zero-sum games and then talk about, because they are completely understood, and then go into Nash equilibria. And he gave me several examples of very hard zero-sum games. So there's actually a lot of still interesting things in zero-sum games that he had studied. Coming back to Tsinghua, so the Minimax theorem of von Neumann was applied in insightful way by Andy Yao in what's known as Yao's Minimax principle that relates optimal performance of a deterministic algorithm on a random input to random algorithm on deterministic input. And he realized that von Neumann's theorem is applicable here, and this has many, many applications in analysis of randomized algorithms. There's a whole book on online algorithms that revolves around applications of this principle. Yao got the Turing Award in 2000. Oops, 10 is missing there. And the Basic Sciences Award, just last year. So there are lots and lots of game theory books. There's one by Myerson. I'm mentioning two here. One that I co-authored with Anna Karlin, who's a computer scientist. She's the daughter of Sam Karlin, who was a probabilist. She's a great computer scientist in Seattle. And there's another much bigger book by, it's hard to read, Michael Mashler, Eilon Solan, and Shmuel Zamir. And both of these books insist on actually proving statements like Brouwer fixed point theorem that are used to do Nash equilibria. So as a mathematician, you can really understand all the principles being used. But certainly, our book is just a few hundred pages, so it only gives you a survey of many topics in game theory, and you have to dive deeper to learn more. So our book is maybe 400 pages. This book is 900 pages, so a lot more information. And these are professional game theorists, so highly recommended, but also mathematicians. So they explain all the math. And then there are dozens of other wonderful game theory books, more from an economics perspective. Finally, my own connection to game theory, besides writing this book, is through a connection to PDE that we discovered with Oded Shram Scott Sheffield and David Wilson. It was published in Duke Math Journal some 15 years ago. And there's a generalization to the P-Laplacian. So anyone, finish in 1 minute. Anyone doing probability knows the connection of random walks to the classical Laplacian, and this is the analog of that for other versions of the Laplacian. And there are several books that came out, expanding on the theory we initiated. In particular, I recommend this recent book by Mikko Parvanen, and I'll end with a picture from his book. I don't have time to explain it, but maybe another time. Thanks for your attention.